So how much energy corresponds to 1 U? This can be helpful as well, because if we get the mass difference, we can compare this to U and do that. So 1 U is 1.6605,402 times 10 to the negative 27th kilograms equals mc squared. We have our mass, we have the speed of light squared. So that's how much energy corresponds to 1 U. If we convert that to electron volts, that's 931.5 times 10 to the 6 electron volts. So that is the energy corresponding to 1 U. If we had a mass defect of 1 U, that would be the energy holding the, whatever that is together. And so, yeah, so again, for 1 U, there's 931.5 mega electron volts of energy. It turns out on your equation sheet, they give that to you based on the different values here. And so, in other words, how much does an electron in terms of equals mc squared equal? We've got that value here for proton rest mass, for a neutron rest mass, and then also for the unified mass unit here. And this is getting this in terms of, yeah, if we have a certain amount of mass in terms of U, we can look at that, the energy corresponding to that mass value. Okay, so how do we practically use that? Well, let's say for our example here, we have a mass defect of 0.030377912. Well, yeah, 1 U is this many MeVs, and so we multiply those, and that's how many mega electron volts is holding the nucleus together. And if you look at the answer that you got before, that's what we got. So yeah, it's just kind of a shortcut way. Either way is fine. But this is a way to just go straight from mass defect, apply E equals mc squared, because really that's what's happening inside here, and then getting the binding energy. All right, so let's say we did this for oxygen. I'll have you try this, so go ahead and pause the clip and get the binding energy using that value there, that like we did in the last one, and then when you're ready to check, you can hit play to continue. Okay, so 123.4 mega electron volts for the binding energy of oxygen. Let's go ahead and try per nucleon. So, and for neon here. And so if we look at that, right, we have our mass defect here, and we can do that. We can take this value, we get this. Now this is for the entire nucleus. So how would we figure out per nucleon? Well, we just divide by the number of nucleons. So there's 8.03 mega electron volts of binding energy per nucleon for neon. All right, so let's say we have our helium nucleus here, and we know the binding energy. We got that before. And we wanted to look at what is it per nucleon. So any given nucleon, a neutron or proton in there, what's the binding energy holding it to the nucleus, holding that nucleus together? Because remember, those protons want to get away from each other, but that nucleus doesn't split apart, right? So we take our total binding energy divided by 4, and that is our binding energy per nucleon there. Now we can compare that to oxygen. Oxygen has 16 nucleons. Here's the total binding energy. We divide by 16, and that's our value there. So if we compare these two, this is, let's get a color we can see here, 7,726,000 versus 7,084,000. So there is more binding energy per nucleon in oxygen, holding that oxygen nucleus together as compared to helium. Now, how about neon? Well, that's the binding energy for neon. Per nucleon, we divide by 20. There's 20 nucleons, adding up the protons and neutrons. And that's even more. We have 8 million electron volts per nucleon binding energy. So what we can do is we can take a graph like this. This is binding energy per nucleon in mega electron volts in the y-axis, nucleon number in the x-axis, and we can plot those. And so if this is in mega electron volts, we have these, we can set this up, and I encourage you to draw this out on your notes, 1 through 9 here. And we can plot these. So let's go ahead and plot the ones that we have so far. We have 4 nucleons here, and then there's our binding energy for 18. There's our binding energy for the 20. That's our binding energy, and yeah. So the question is, what do you think is right here? What's the binding energy up here? And so that has the most binding energy per nucleon. And to think through this question, you could say, okay, what's the most stable element in the universe, or what's among the most stable elements in the universe? Because the more binding energy per nucleon you have, the more that nucleus wants to hold together, and the more stable it is. So if you look at this graph, you can see those. Up here at the very, very top, you have the elements that have the highest binding energy per nucleon out of this whole graph. And you'll probably recognize some of these things here, right? You know, you've got iron, you've got nickel up there, and strontium is a little bit to the right there. Okay, so yeah, iron is one of the most stable. It turns out nickel is extremely stable as well, and copper there, okay? Now, uranium-238, interestingly, it's all the way very, very far on the right. And so, again, binding energy per nucleon, it's not as stable, right? So, you know, we can compare those to the others, but yeah, again, it's not stable, not as stable over there. All right, so nickel, right? Nickel is extremely stable, and this will be a good chance to review, you know, the binding energy and figuring that out. So here's our values here. Z is 28, A is 62. We have our atomic mass, and if we subtract out our electrons, we can do that, find the binding energy per nucleon in electron volts. And so, yeah, so we take the, we know it's 28 electrons. We can subtract that out, subtract the mass out from the nucleus to get the nuclear mass, and there's the nuclear mass. So yeah, go ahead and take it from there. Go ahead and determine the binding energy overall, and then the binding energy per nucleon for nickel for this particular situation with nickel, with this number of protons and neutrons. And then, yeah, go ahead and pause the clip, and when you're ready to check, you can hit play to continue. Okay, so 28 protons, 34 neutrons, and we get a total mass of 62.49834.793. We can get our mass defect, the mass apart versus together, and again, together here is the value given right here, and then apart we've got there. So there's the mass defect, and we can convert to kilograms. Equals mc squared. We get our binding energy in joules, and we can convert to electron volts, divide by 62, because there's 62 nucleons. And so there we go. This is 8,807,696.764 electron volts binding energy per nucleon. So very stable. This nucleus, you know, wants to stay together. All right, so let's take a look at this picture now and compare the left side to the right side. Well, on the left side and the right side, we have the same number of neutrons and protons. But on the right-hand side, we have an alpha particle shooting out. And so if we look at that, right, as soon as the nucleus just splits apart a little bit, the electromagnetic repulsion just takes over, and then they split apart really rapidly, right? Because the strong force, the strong nuclear force, doesn't act over a very long range at all, very small range, right? So these subsequent nuclei, the helium nucleus, which is the alpha particle here, will split apart from the original nucleus very rapidly, and they'll split apart. So let's take a look at what happens then with the energy, because we know that the nucleons apart are different than together. Here's radium to radon, so we have radium 226 and then radon, and and then an alpha particle shoots out. And so what we want to do is we want to find the difference in mass before and after, and then that will be the kinetic energy given to the particles after the decay. Because remember, as mass and energy equivalence here, right? Because, you can't just separate one from the other. We're going to get a difference in mass here. The radium together is going to be a different mass than adding these two up, because you're going to have some energy left over afterwards, and that's going to be given to the particles. Now, here's an important note here. As long as the electrons are there before and after, you can actually leave the full atomic mass. You don't have to subtract the electron mass from any of these. The helium nucleus obviously won't have any, but radon will, right? We'll have the electrons there. So yeah, you can just leave the electrons there. So so what we can do then is we can take a look at the mass before, which is 226.0254 U. We can get the difference in mass. Afterwards, it's radon plus helium. And we can get the mass defect. We'll subtract the two. So this is the difference in mass before and after. Therefore, if we get that mass in kilograms and we use E equals mc squared, that energy will come out to be this, and that is the kinetic energy of the particles. So in other words, you have that radium just sitting there. When it alpha decays, the radon and the alpha particle have this much energy as they split apart, and they're moving. They have a kinetic energy, right? And so that mass that's lost is turned into energy, and it splits apart, and those particles move apart.